All right, other for what do chemists do? Yeah, predict what kinds of reactions will occur. In other words, chemists are interested in the properties of matter, and when we think about the properties of matter, well, what types of properties? They could be interactions. Interactions would be things like intermolecular forces or solubility or those types of things. They could be interactions like that. Could be interactions within matter, like if you need to melt it or get it to dissolve, right? Or it could be actual reactions between different species. And so we're interested in the properties of matter. And when we think about properties, how many different types of properties are there? Well, there are lots, right? But we classify those into two major types of properties. What are the two major types of properties? This is just a review from chapter 1. What are the major types of properties that chemists study? Well, the state, it could be the physical state. The physical state, you can list a whole bunch. The physical state, density, boiling point, melting point, all those. All those would be categorized as what type of property? Physical properties. And then we have chemical reactions, studying the chemical reactions between matter. That would be an example of chemical properties. And so we're interested in the properties of matter, and there are different ways to understand the properties of matter. One way of understanding the properties of matter is just go through and tabulate them into some table or into some book, and just have a list of properties for different substances. You can do that, or in other words, we could just take a lot of observations. Observations are usually measuring the properties. When you observe nature, you measure its properties, whether it's the state, or its density, or its boiling point, or its chemical reactions. Right? We're measuring that by observing these reactions or observing these properties. And so we could compile a whole list of experiments to conduct, and then conduct those experiments, and then we can go through, and if we wanted to, I guess we could memorize certain properties, like I'm sure you've memorized certain properties of water or whatever else. Right? But when we think about the properties of water or any other compound, yeah, we can measure those properties, like the boiling point of water is 100 degrees C, and freezing point is 0 degrees C. But rather than measuring those, we might also want to take a theoretical approach. So would that be easy to do? A theoretical approach to, okay, predict the boiling point of ethanol. Are you going to use theory to do that, or are you probably just going to do an experiment to do that? You're probably just going to do an experiment because it's a heck of a lot easier, right? But that's not to say that theory can't help us, because there's some theoretical stuff that can be very useful in understanding properties. And it wouldn't be the full rigorous, what's that theory of chemistry, the theory that underlies chemistry called? What's the theory that forms the foundation of chemistry called? Is it called atomic theory? Well, yes and no. I mean, chemists deal with atoms, but really, why are some atoms different than others? Why are the properties of some atoms different than the other? And it has to do with well, equilibrium is just a process. It's not really well. It has to do with the composition and the structure. And what tells us the structure? When we look at it, does the nucleus tell us how something is going to react chemically? Did you know when you drink a cup of water, are all the water molecules that you just drank identical? True or false? False. Not all the water molecules are identical. Well, if they aren't identical, how do they differ? What makes the water molecules different? No, the water molecules aren't identical. Just like when you inhale oxygen, O2, are all the atoms that make up the oxygen identical? No, and the reason is because of isotopes. What were isotopes again? Isotopes are the same element, but different number of neutrons, right? And so what I did was, when I drank this cup of water here, some of the oxygens I just drank were oxygen 16, some were oxygen 17, and some were oxygen 18, right? If I drink an oxygen 18, is that going to kill me? And then some of the hydrogens were hydrogen 1, and some of them were hydrogen 2, which we call deuterium. And so I just drank some deuterium. Am I poisoning myself? No, because, the chemical properties aren't dictated by the number of neutrons you have in the nucleus. The chemical properties are going to be dictated by the number of electrons in the nucleus, and what dictates the how the electrons. In fact, what we're interested in here is when we look at this, and we're chemists, some things will help us. Some of the things are like how the electrons are arranged in the atom, and how the electrons are arranged in the atom we can see here using the periodic table. The periodic table is based on what? Filling these orbitals with electrons. Where do orbitals come from? We talked about orbits versus orbitals. Remember, orbits were part of the Bohr model. That was abandoned. The Bohr theory was replaced with what theory? This is why I say, for your notes, what you want to do is you want to have some kind of take-home message. So yesterday, what were the key points from lecture? Well, you should have like a little list, or you should annotate your notes saying some of the key points. And one of the key points from yesterday would be that the Bohr theory was abandoned and replaced with quantum mechanics. Quantum mechanics dictates how the electrons are placed. Well, that's everything in chemistry. So the theory that underlies chemistry, that is, the theory underlying this periodic table of elements, is quantum mechanics. And what do we, us chemists, use to figure out properties? Well, we use this type of stuff. And so properties, we're looking at this. But, theory, I presented theory in different ways, and we could take advantage of theory at different levels. So one level we can use theory is just using the periodic table and figuring things out from that. And so, or another level would be when we look at properties, we want to know certain things. Like, for example, graphite versus diamond. They're both made out of carbon, but are the properties of graphite the same as the properties of diamond? No, they're totally different. And so why are they totally different? It's because even though they're made out of the same thing, their structure is different. And so what we're going to do at a different level here is when we use theory, we try to understand this using composition and structure. And composition and structure, we don't have to do full-scale quantum mechanical calculations. We can figure out composition and structure using periodic table and other things we've learned along the way, right, to figure these types of things out. And so this is what chemists are trying to do. They're trying to figure out, why does this have certain properties? Well, we look at it, what it's made out of and how it's built. I saw an interesting illustration or model. Let me just show you on the computer here. In the LA Times recently. You might have seen this published somewhere else. But this came out over the summer. This is for the Zika virus. So if you want to understand some of the properties of the Zika virus, you want to understand what it's made out of and, right, how it's structured. And so this was pretty interesting because this is a model of the composition and the structure of the Zika virus here. But we do the exact same thing, but rather than looking at viruses like this, we look at molecules or compounds, you know, that is solid state lattices, etc. And so we do just the same. So let's see. Here. So chemists are going to try to understand the properties of matter based on composition and structure. All right, so to do that, well, there are two approaches we could take. One approach is this. If I'm looking at the properties of HCl, I can just test that. You know, I can take some HCl, I can figure out its boiling point, melting point, all these types of things. And then I can take some HCl and start reacting that with different chemicals. So what does HCl react with chemically? It takes sodium hydroxide, check, yes. Lithium hydroxide, yes. Barium hydroxide, yes. and then, excuse me, go down the list. And so test those individually, but that turns out to be quite a huge task. And so doing this straight from observation would be difficult because you'd have to observe every interaction that HCl has with other matter. Is that going to be something? No, that's not going to be possible. And so we don't approach it strictly from observation, but do we approach this theoretically? Well, what's the theory of chemistry? The theory of chemistry is quantum mechanics. Are you going to be sitting there doing quantum mechanical calculations? You know, quantum mechanically calculate the boiling point of HCl for me. Is that something that's going to be easy to know? Quantum mechanically calculate, I mean, it's doable, right? You could do it, but it's too much. And so what we do is we try to use as much theory as possible. Now, it's not necessarily rigorous theory, you know. We know things like, well, HCl forms molecules like this, and we can use a Lewis structure like this. Lewis structures, where did Lewis structures come from? Lewis structures come from this whole idea of valence electrons, right? Valence electrons come from this whole idea of the periodic table, which comes ultimately from quantum mechanics. And so here's how we're using the theory. We know some of the theory already. In fact, this bond here, you know, is described quantum mechanically, but when we think about just bonding alone, there are actually, how many bond theories do you recall from Chem 1A? You know, if we're just to describe the bond here, do you recall that there are two bonding theories? Right? Do you remember the name of the bonding theories? Their names? Valence bond theory and the other one, molecular orbital theory. And so the question often comes up, why are there two bond theories? In fact, what is the difference between valence bond theory and molecular orbital theory? Do you know the difference between valence bond theory and molecular orbital theory? Why do we have two theories to describe a bond? Don't we just need one theory? Or are two theories really required to describe a bond?
Is it because that the atom can only be structured a certain way, so you needed to formulate how to see that, and then the valence bond theory shows you how it goes into like the different shells?
Different shells.
Is that
well, it's not entirely wrong, but it's not really right either. I mean, there's certain aspects of that are correct.
Molecular orbital theory can describe the shape of the molecule, and valence bond can describe how big the
Not really. Both describe the shape of the molecule. Valence bond theory, if you recall valence bond theory, you'll have like a sp3 carbon. sp3 carbon will have a tetrahedral set of sp3 orbitals. You know, that describes the shape of these things, and when they bond, they can form a tetrahedral molecule, if we're going to trigonal pyramidal molecule, or it can form a bent angular molecule, right? That all comes from valence bond as well, this structure. In fact, let me go back to this. Lewis structures come from valence bond theory. Vesper, you know, valence shell electron repulsion theory comes from valence bond theory. That type of stuff. What's that? Hybridization? Hybridization occurs in both theories. Although in the molecular orbital theory that you covered here, you didn't do hybridized orbitals. But you could use hybridized orbitals in molecular orbital theory, just like you can use hybridized orbitals in valence bond theory. You just didn't do it. That's true. That's true. So which is correct? Localized or delocalized, or are they both correct? Or when do you use valence bond theory and when do you use molecular orbital theory? Okay, you would use valence bond theory to do VSEPR, in which you could predict the shape and some of the properties. That's true. We use VSEPR to do that. We could also use molecular orbital theory to do that. And so the point is this. The point is when you go back and review your notes, what you do is you just don't read them, but as you're reading them over and over again, pretty soon you start to formulate, well, what was the point of that chapter? What was the whole point of that bonding chapter? The whole point of that bonding chapter is to tell you about two bonding theories, right? And those two bonding theories were valence bond theory and MO theory. The whole point of that chapter was to tell you the difference between the two. And, okay, the difference between the two. Valence bond theory treats a bond as overlap of atomic orbitals. Molecular orbital theory treats a bond as the linear combination of atomic orbitals to form new molecular orbitals, right? Okay, and the point of that was to tell you this. Valence bond theory had some major failures. The biggest failure of valence bond theory had to do with a very simple molecule. It could not predict the properties of this molecule correctly. What molecule was that? O2. You remember what was it about O2 that valence bond theory failed? Yes, right. O2, they show, in that chapter, they show a figure of somebody who poured liquid oxygen between the poles of two magnets. Do you remember that figure? And so what you do is you cool down oxygen until it liquefies. Liquid oxygen is pretty dangerous. You don't want it to come in contact with organic material because it could cause an explosion. And so you pour liquid oxygen, and the liquid oxygen gets trapped between the poles of the magnet, so it's like floating in air. Do you remember that figure? And so, that's very important because that means valence bond theory failed to predict. What should theories do? Theories should be able to predict, right? Valence bond theory failed to predict that oxygen is paramagnetic. And so tell me this. Since valence bond theory failed to predict that oxygen is paramagnetic, we abandoned valence bond theory just like we abandoned Bohr theory. True or false? False. Then the next question comes up. Why don't we abandon valence bond theory? Why? It doesn't make sense. We abandoned Bohr theory because it couldn't predict helium. We should abandon valence bond theory because it can't predict O2. And not only that, it predicted localized electrons for benzene and for ozone and for other molecules. Valence bond theory failed, but we did an ad hoc modification. Ad hoc means after the fact modification of valence bond theory. The ad hoc modification to valence bond theory that we did was we came up with the concept of the resonance hybrid. Remember that? You do the resonance hybrid, then everything's okay again. But if you did just the resonance forms, well, that's not right because it's not this one, it's not that one, it's a hybrid of the two, right? And so with these failures of valence bond theory, then it should be abandoned, right? Yes, it should be, but why wasn't it abandoned? Why did they teach you valence bond theory, which clearly failed for oxygen? And they didn't teach it like the Bohr. I think they clearly stated the Bohr model was abandoned, right? There's no such thing, at least in modern day jargon, of talking about orbits. We don't have orbits for electrons. We have orbitals. And so in one respect, well, both valence bond theory and MO theory both have orbitals, so that's good. But somebody tell me why valence bond theory was not abandoned. It has some failures, so looking back at Bohr, I can make the connection. Bohr was abandoned, valence bond theory should be abandoned. It should be abandoned, but the reason that it is not abandoned is because yeah, it gives approximately the right answer with a lot less work. And so the reason it's not abandoned is because MO theory is too difficult. That's why. MO theory is the full rigorous quantum mechanical approach to bonding. Valence bond theory, you could classify that as quantum mechanics light. You know, molecular orbital theory would be full quantum mechanical treatment. Valence bond theory would be the simplified quantum mechanical treatment, where they make some simplifications so that they can do the calculations, right? But it doesn't always give the right answer, but the answer comes out kind of close, you know, when you compare the electron density distributions from MO, like, you know, when you look at ozone and you do the resonance hybrid, and then you look at ozone and you do the MO, the kinds that comes out close, pretty close. And so it's not it wasn't abandoned. The reason it isn't abandoned is because it's very useful, but it does have its limitations, right? And so as long as you're aware of those limitations, then you're okay. You just don't treat it as the end-all theory, which MO would be. Well, going back to this, well, you know, we make simplifications. We don't use the full quantum mechanical, but we try to be as rigorous as possible in our understanding of composition and structure, particularly structure, because, you know, structure is very important. How things are bonded together will deeply impact how its properties are. Just looking at diamond versus graphite, you know, the same exact composition, carbon atoms, is different structure. And so this is kind of our approach. You know, we try to mix in some factual knowledge and some theoretical knowledge to come up with a more complete understanding of properties. So we'll just go through some of the PowerPoints. I already talked about some of these slides, so I'll just go and skip those. But here's the definition of chemistry from the American Heritage Dictionary. The composition, structure, properties, and reactions of a substance. And so I just take this as the composition, structure, and properties. Chemists, you know, this dictionary divides this into two. And reactions are properties as well. And so what they're talking about, they must be implying physical properties versus chemical properties here. But a chemist would just define it as the composition, structure, and properties of matter. That's it. I think not just chemists are interested in this, but you can see biologists are interested. Why would they care about what the structure of the Zika virus is? You know, what it's made out of, what the different components are. You know, because it's gonna have a big impact on the properties. So all the scientists, the engineers, mechanical engineers, etc., are interested in, you know, what is going to alter the properties, or how are the properties dependent on these two factors. So the goal of chemistry, as well as much of science, is the understanding of the properties based on structure and composition. And obviously, we try to use as much information as we have. And so, you know, we have theory and descriptive. The rigorous theory is quantum mechanics, but, you know, it's not just quantum. From quantum mechanics, we get the periodic table. From the periodic table, we get lots of other stuff, Lewis structures, etc., Vesper. And so we could use that. And the theory doesn't always have to be doing mathematical calculations. The descriptive part is just doing measurements and observations, experimental facts, as we call And so an example here is HCl, a gas, liquid, or solid at room temperature. Well, the easiest way to describe this is using descriptive chemistry. You know, it's just easiest to have HCl memorized as a gas. You know, you could draw out the Lewis structure, but is the Lewis structure really going to tell you if that's a gas, liquid, or not really? Then you'd have to go to quantum mechanics, but you could do different levels of quantum mechanics. You know, because ultimately, chemistry deals with electrons, right? And electrons have charge, and these charges are going to dictate a lot of the properties. So ultimately, all chemistry depends on electrical interactions, which we'll talk about more in detail later. So we could do full quantum mechanical. Quantum mechanics, you know, when we're talking about orbitals, it shows us how the electron density is distributed in the molecule. Well, how that electron density is distributed will show us how the charge is distributed, because electrons are all the negative charge of the molecule, so it shows us how the negative charge is distributed. The positive charge is within the nucleus here. All right, so this is best answered using descriptive chemistry. We could use a little bit of theoretical knowledge to figure out HF versus HBr. Would HF also likely be a gas? Yeah, here we would think in terms of intermolecular forces. You know, what causes HCl to become a liquid is the electrical attractions. It would be a dipole attraction. You know, the delta plus, delta minus is being attracted to the other ones. And so if we look at those attractions and compare them to HF, the dipole attraction should be stronger. If the dipole attractions are stronger, then maybe this should be a liquid. But in addition to dipole attractions, we also look at instantaneous dipole attractions. Instantaneous dipole attractions are called London or dispersion forces. When we look at instantaneous, chlorine is not very polarizable. Bromine is much more polarizable. Why is bromine much more polarizable than chlorine? Yeah, it has a bigger electron cloud. The bigger the electron cloud, the more polarizable it is. The more polarizable it is, the bigger the instantaneous dipole you can generate, and the stronger the London force is. What's stronger, London dispersion forces or dipole? Which one's going to dominate the properties of HCl, HBr, HI? It turns out that this, you know, we can use some theory, right? It turns out that, well, I don't know. You know, I don't know. Which is stronger, dispersion or dipole? It depends on the molar mass. And so, do you see, I'm running into a bit of trouble here, because HF versus HCl, which one has a stronger permanent dipole? Fluorine or chlorine, which one's more electronegative? Fluorine's more electronegative, so this one's going to have a bigger permanent dipole. Chlorine's going to have a smaller permanent dipole. And so chemical interactions are electrical in nature, so two HCl's come each other, they see smaller charge. Two HFs come together, they see larger charge. What gives a stronger electrical interaction? Bigger charges or smaller charges? Bigger charges. Do you guys remember Coulomb's law? Coulomb's law, we should recall from chapter 2, that the force of attraction or repulsion is going to depend on the charge on body A times the charge on body B divided by the distance between the center of charges squared. And so the higher the charge, the stronger the force. And so we expect, this should have a stronger force of attraction between the molecules. Stronger force of attraction means this should tend to be more liquid or solid-like, because solids and liquids have stronger attractions than gases do, right? But do you guys remember the boiling point chapter? The intermolecular forces chapter? Which one has the highest boiling point? Is it HF with the biggest dipole or HBr? HBr has an even smaller dipole because bromine is the least electronegative of the three, right? And so do you guys remember this from that chapter? Based on this, I would say HF has the strongest or intermolecular attractions, which means it's going to be harder to break apart the molecules. If it's harder to break apart the molecules, you're going to need higher temperatures. If you need higher temperatures to break apart the molecules, the boiling point is going to be higher. And so I expect HF to have the highest boiling point, but if you recall that chapter, it was wrong. In the chapter, you saw that it wasn't HF, it was indeed HBr. Now, why did HBr have the highest boiling point, not HF? Because, well, they use weight. I know they use weight. They use the molecular mass or the weight to get a gauge of the dispersion force strength. And so they put the weights here, the molecular masses here next to this. But it turns out that it's because of the number of electrons. And so if it weighs more, it's got more electrons. If it has more electrons, it's more polarizable. And so the reason is because this is the most polarizable, and so this could create a bigger instantaneous dipole. So if the electrons are polarized one way, let's say the electrons get polarized towards hydrogen, then the instantaneous dipole in one instant can be much larger than the permanent dipole. And then the electrons move back, the instantaneous dipole can shrink. You know, but these fluctuations in the electron cloud create large asymmetries in the electron cloud distribution, which results in larger instantaneous dipoles. And so the thing is that we can use theory up to an extent, because looking at this, the highest boiling point using permanent dipoles would be predicted to be HF. This would have the highest boiling point, this would have the lowest boiling point. The highest boiling point using London forces would be HBr. HBr should have the highest boiling point. HF should have the lowest boiling point. So we have a conflict. Dispersion forces tell us HBr. Dipole forces tell us HF. Who's the winner? Well, who's the winner is you could calculate that using quantum mechanics, but is that something you're going to do? No, so the best thing is you memorize it. You have to have stuff memorized. Otherwise, you would have no idea. I don't know which one's stronger, but you know what? I memorized it. I memorized that HBr has the highest boiling point. Therefore, I can conclude that the most important is not the permanent dipole. The most important is the dispersion forces. So dispersion forces are more significant in this series than dipole forces. And so this is our mix. Yes, we could have figured that out purely theoretically, but no way would we have actually done that. Instead, we would have used a mixture of fact, that is experimental fact, is that HBr has the highest boiling point, and theory. The theory here left it ambiguous. We didn't know which one it was. And so we need certain points referenced in our memory so we can anchor things in. We don't always have those reference points anchored in. So for example, if somebody told you, hey, a carbon-carbon bond is 347 kilojoules per mole, does that mean every single carbon-carbon bond in existence has that bond? No. In fact, there's going to be a variation. You know, some carbon-carbon bonds are going to be a little weaker, some are going to be a little stronger. And so do you know what the weakest would be, and do you know what the strongest would be? Do you know what the range is, right? No, all you know is one data point. You have no idea what the whole range is. And so that's a problem. So what we do in science is we try to memorize things like a range. You know, this is a range of reasonable values. And so it should fall somewhere in between the two extremes. You memorize the extremes and then we have it. Rather than memorize the average. If you memorize the average, you don't know what the extremes are. This is like a homework. Some people will spend 3 hours doing one homework problem. But, you know, homework is like a forest. You know, there are little ones, big ones, variations, right? And so if it's like a forest and all you're doing is spending all your time studying one problem, you have no idea what the breadth and range of the problems really are, right? And so the good thing for homework is to do a shotgun approach. What you do is you try to expose yourself to as wide a range of homework problems as possible. That way you get a better idea of what the extremes are, you know, and the variations in that. And so, well, what we're going to do is we're going to do this kind of mixed approach for chemical reaction. For chemical reactions, we try to, you know, use theory when we can to better understand things, but we also rely heavily on memorization as well. And so let's start off with HCl. Let's talk about the chemical properties of HCl. What are the chemical properties of HCl? Well, a lot of people say HCl is a strong acid. You know, it can neutralize bases. But is that it? Is that the whole forest, or is that just one tree? Well, a lot of people will just focus on one tree. They'll say HCl neutralizes sodium hydroxide. Well, if it neutralizes sodium hydroxide, can it neutralize potassium hydroxide? Yeah. Can it neutralize other hydroxides? Yeah. Can it neutralize other bases? Yeah. And so what we'll do is we'll kind of zoom out and then see. Yeah, HCl reacts with sodium hydroxide, but it reacts with all hydroxides. Right? Not only that, HCl will react with other bases that aren't hydroxide. So what we could say is we could say HCl reacts with bases. Is that it? Is that the full spectrum of HCl reactions? Well, it depends. We could go by, you know, bit by bit. You take HCl and grab each bottle. Do you see all the bottles and the hoods there? We can grab a test tube of HCl or multiple test tubes and then start adding drops of chemicals and see which chemicals it reacts with, right? But that's too much. So what we want to do is we want to use that mix, and that mix is trying to use patterns of reactivity that we've seen before. And the patterns of reactivity that we've seen before are this. There are 3 types of chemical reactions. You're just taking my word for this because you haven't seen enough, you know, to categorize. I mean, if you've seen a lot of reactions, then you could make the categorizations yourself, but you're just taking my word for it. And so what we want to do is we want to get you comfortable. I want to get you comfortable with these categories by showing you examples of the different types of chemical reactions and figuring that out. And so here, HCl reacts with strong and weak bases. This reacts with any base, pretty much, most bases. Not all bases, maybe the most. Some bases it won't react with are extremely, extremely weak bases. What else? Well, you probably saw that HCl reacts with magnesium. Did you do this experiment in Chem 4? If you took Chem 4 here, you would have generated hydrogen gas by mixing magnesium metal and HCl. But not only does it react with magnesium, it reacts with aluminum, it reacts with all what we call active metals, lead, etc. And so it reacts with metals like that. In other words, here, most people only look at the acid-base properties of HCl, but what other properties are there? There's redox. In redox, it's reacting with the metals like magnesium, aluminum, whatever else, and metathesis. Metathesis. What metathesis properties are there? Well, we got to look. You know, we have the H plus ion and the Cl minus ion. H plus ion likes bases, anything that is a proton acceptor, so that kind of falls into this category. But what about Cl minus? What does Cl minus like? You know, metathesis are double replacement type reactions. In other words, ion combinations. When you're doing double replacement, you're switching ion partners and then seeing if those ion partners like each other. If they like each other, then there's a reaction. If they don't like each other, then there's no reaction, right? And how can we tell when the partners like each other? We can tell by if they form precipitate or a gas or whatever else. But in terms of metathesis, yeah, HCl like silver ions. If you have silver ions present with HCl, you're going to precipitate out silver chloride. HCl likes lead-2 ions. If you have lead-2 ions, you get a white precipitated PbCl2. HCl likes mercury 1. So if you have like mercury 1 nitrate acetate, you mix that with HCl, you're going to get a precipitated mercury 1 chloride. And then, so that takes care of acid-base redox metathesis. Is that it? Have we covered the full forest of reactions? Or are there a bunch of reactions that we might have missed? The reactions we might have missed that are hidden somewhere? No. And so this is why we categorize it in this way. No, we've covered it. This is it. These are the three basic types of chemical reactions. Now, are you going to sit there and go, what decomposition reactions does HCl undergo? What combination reactions? What precipitation reactions? What neutralization reactions? No, you could go on through a series like that, but this is basically it. The three basic types, and then we covered it. There are some that actually fall outside. Combustion, I forgot combustion. What combustion reactions does HCl undergo? But anyway, these were the lists that you have from Chem 4, Chem 1A. And is that a comprehensive list? It's not a comprehensive list either, because let's take a look at this first reaction here. From Chem 4 or Chem 1A, what would you categorize this reaction as? This is HCl with HNO3 with gold. What kind of reaction is that? Is that double replacement? Single replacement? Combination? Decomposition? Neutralization? Combustion? No, it doesn't fit any of those categories. So we have to have another category to add on top of that. Whereas this one does fit ours. You know, this is a combination reaction of redox and acid-base. But this is a very famous reaction, a mixture of HCl and HNO3. This is called aqua regia. But you go, why are you mixing two acids? This is a strong acid, this is a strong acid. These two strong acids are not the same. When I look at these two strong acids, I go, wow, those are totally different. Those are totally different in one type of reaction. As far as sodium hydroxide goes, sodium hydroxide care less if it's HCl, HNO3. If you're trying to neutralize sodium hydroxide, it makes no difference. They're going to react exactly the same. But when I look at HCl and HNO3, I see things that are different in the composition and the structure of these two. And therefore, HCl is what I term a mineral acid, but HNO3 is a special acid. HNO3 is what I'd call an oxidizing acid. It's an oxidizing acid because the oxidizing properties, or the oxidizing strength of HNO3 is different than HCl. HCl, when this attacks metals like magnesium, the H plus will take the electrons from magnesium or alumina or whatever else. But when I look at HNO3, it's a nitrate. That's a little bit different. But anyway, this is royal water, and these two acids serve different purposes. And they're used in different ways. And this is because the chemical properties of these two acids are different. So we have aqua regia. The special thing about aqua regia is capable of dissolving gold. And so this is a very famous reaction because gold is notoriously difficult to dissolve. And so one way we can dissolve it is use royal water. But the raw water, it doesn't stay as gold, you know, it forms different products here, but you can recover the gold afterwards by reversing some of the reactions we have. All right, so the problems with the previous list, you know, is it's not comprehensive. If we go down that list, we might have missed a reaction that could potentially occur. That's not good, is it? If we want to catch the whole forest. This will catch the whole forest. Even though it's a shorter list, the categories are a little broader, and we don't focus in as much. Okay, the other thing is confusing, because if you look at this, this is A plus B yields C. A plus B yields C. So both of these reactions we term as combination reactions. A plus B yields C reaction, right? In Chem 4, they didn't do this in Chem 1A, but in Chem 4 they subcategorize this. This is called an element plus element combination. So you memorize those. And then you memorize the compound plus compound combination, and then you'd memorize the element plus compound combination reactions. Yeah, do you want to memorize all those subcategories and then go through all those? Because I didn't even write those on the previous slide. No. And so here, this is confusing. The reason you might say that's not confusing. This is very simple. A plus B yields C. A plus B yields C, right? No confusion there at all. But what's confusing is this. What's confusing is when we're looking at reactions, we have something called the driving force for the reaction. The driving force for the reaction is what's driving that reaction forward, you know? It's what's causing the reaction to occur. That's what we call the driving force. And the reason why this is confusing is because what drives the first reaction is completely different than what drives the second reaction. The first reaction, what's driving that is, well, what is driving that? Well, what's driving that is this. These three types are based on driving forces. All acid-base reactions share the same driving force. It's the same thing pushing the reaction forward, as do all redox, as do all metathesis. Sometimes there's some overlap between metathesis and acid-base, right? Or overlap between the other categories. And so these three types are based on driving force. Whereas a combination reaction is not based on driving force. These two combinations are totally different. This is why you had to memorize, and if you took Chem 4 here, this is why you had to memorize so many subcategories of combination reactions, which is ridiculous, I think. And so it's confusing, too, because even though both are combination, they're totally different reactions. And so this is the alternate based on driving force, metathesis, acid-base, and redox. There are others. Is it really a comprehensive list? No, but these are the major types of reactions. We have other ones like photochemical reactions involving free radicals and other stuff. Okay, that can be part of this or can be outside of this, depending on how it reacts. But we aren't going to cover those in depth. We're going to cover these in depth because when we take two bottles of reagents off the shelf and mix them together, we want to know or have some kind of idea of what's going to happen when they're mixed. All right, essentially, what is a driving force? A driving force is this. In Chem 1A and the first part of Chem 1B, this is what we're going to use for the driving force, and that is we're going to form more stable products from less stable reactants. And so one of the driving forces in acid-base reaction, and this is the driving force, is we want to go from an unstable acid to a stable acid. Now, we understand acids based on strength, like strong acid, weak acid. Okay, in terms of stability, a strong acid is more stable or strong acid is less stable than a weak acid? Which one's more stable, weak acid or strong acid? More stable, less reactive. Strong acid or weak acid? Weak acid. And so the driving force is very simple. For acid base, we go from stronger acid, which is less stable, to weaker acid, which is more stable. If you were forced to drink an acid, somebody gave you some HCl and another person gave you a cup of vinegar, what would you drink? The vinegar, right? It's a weaker acid, but be careful because, that's just acid-base properties. If somebody gave you a cup of HCl and another person gave you a glass of HF, what would you rather drink? You go, I'd rather drink the HF because HF is a weak acid. HCl is a strong acid. Would you want to do that? I see you guys shaking your heads. No? Why not? Because HF is a weaker acid. HCl is a stronger acid, so I'd rather drink the weaker acid, HF. And the answer is, well, they already know. The answer is, it's not the acid. The HCl is definitely going to burn more, but it's the HF, metathesis properties, that are the problem. What happens with the HF is, if you spill HF on your skin, it doesn't burn as much as HCl. But what happens is, let's say the HCl penetrates your flesh and then hits the bone. Well, it hits the bone, it's still going to burn because it's an acid, right? But when the HF penetrates your flesh and hits the bone, do you know what happens? It starts to precipitate calcium fluoride. The precipitation of calcium fluoride is so painful, it could cause death, I think, basically. And people have died from that. But the thing is, how can you wash it off? It's already penetrated your flesh. It's already precipitating on your bone. How do you wash it off? You don't. And so people who work a lot with HF, and HF is used a lot in the semiconductor industry for etching glass. They have injections of calcium, I think calcium succinate or calcium glutamate, and the calcium gets in your blood, and hopefully that precipitates out the fluoride. It's the metathesis that's the killer in HF, even though it's a weak acid. So this is why you just don't focus. Whenever I ask somebody what the properties of HCl are, they just focus on the acid properties. They ignore the redox and they ignore the metathesis properties. Well, it turns out HCl is not. So the same thing for that. And so we're looking and going from, well, the way we're going to treat it here is in terms of the thermodynamic driving force, we're just looking, okay, HF versus HCl. HF is a weaker acid, therefore it is more stable. In terms of acid properties. I'm not talking about metathesis. Metathesis properties, it depends on what else is in there. Okay, so what types of things do we look for? We look for weaker acids forming from stronger acids. We look for precipitates. Precipitates are usually stable. We look for gases. Gas formation is usually stable. We look for certain descriptive stuff to happen. Okay, I'm going to skip this here. And so when we predict these reactions, we're going to start off with a couple of basic assumptions here. The basic assumptions are, one, the concentrations are just kind of average concentrations or normal concentrations. 1 molar for the gases, not gases, 1 molar for the solutions, and the gases are going to be at 1 atmosphere or 1 bar. 1 atmosphere and 1 bar are very close to each other. And so if we have 1 molar, do these conditions sound familiar? Is something from the past that you've seen this before? I mean, can you make a connection with something you've seen in Chem 1A with this first line? And I think it would be chapter 7, maybe? Do you remember these, delta H, with a little superscript? What does that little superscript mean? Standard conditions. This is what we call standard thermodynamic conditions. What are standard thermodynamic conditions? Are standard thermodynamic conditions the same thing as STP, standard temperature and pressure? No, they're different. And so, how are standard thermodynamic conditions defined? Okay, to create 1 mole, you're thinking about this, the little f here. If I had the little f there, you're right. We're creating 1 mole. It would be the formation of 1 mole of substance from the elements in their standard state. But we don't have to have that little f. We don't have to create 1 mole. We can create 10 moles. We can create however many moles we want, and we can still use this little superscript. And that little superscript means one thing. It means standard thermodynamic conditions, which means what? It means that the solutions are at 1 molar and the gas pressures are at 1 bar or 1 atmosphere. That's what it means. And so this is just standard thermodynamic conditions here. But we don't have to be exactly at standard thermodynamic. We just want to be around, around 1 molar and 1 atmosphere, and that's close. The reason why is because if we start changing, let's say we go from 1 molar to 16 molar, what would you rather drink, 1 molar acetic acid or 16 molar acetic? Probably 1 molar, right? Because it would be less harmful. And so the concentrations can have a big impact. In fact, the concentrations can have an extreme impact on the reactivity. So let's take a look at this. Extremely low or extremely high concentrations may require compensating for. And so if we look at this first reaction, which is a double replacement, it's just HCl plus silver nitrate, the standard AB plus CD. What does it yield? It yields silver chloride and nitric acid. And so silver chloride we know is a precipitate, therefore this double replacement reaction should proceed. The driving force is precipitation of silver chloride, a stable precipitate. But if you do this reaction under very dilute concentrations of HCl and silver nitrate, nothing happens. You get no precipitate, even though you have HCl and silver nitrate present. And so the concentrations can have a big impact. In fact, if we did this with lead, it's even worse. You can't go much lower with lead, otherwise you're not going to see any precipitate at all. And so you might be expecting to precipitate, but get nothing. Well, it doesn't mean it's not there, it just means maybe the concentrations are too low to detect or to observe a reaction. All right, the other thing is not only can concentration have an impact, but also temperature. And so when I was in Chem 1B, we had to do a project. And the project was this. The project we had to do was we had to convert silver chloride solid into silver nitrate solid. And so how do you convert silver chloride into silver nitrate? Well, one thing I was thinking is let's just do double replacement reaction. The double replacement reaction would just be silver chloride solid plus nitric acid and just swap the anion. So what we'd end up forming would be silver nitrate plus HCl, right? But there's a problem with this reaction. What is the problem with this reaction? This is aqueous. What is silver nitrate? Nitrates are aqueous too. All nitrate salts are soluble. What about HCl? HCl is aqueous. Therefore, we have no precipitate. But just because we have no precipitate doesn't mean we won't have a reaction, because we could also look for formation of a gas. Are either of these gas? Not really. HCl can be if you heat it up, but at room temperature it's going to stay that way. Or going from a stronger acid to a weaker acid, because we know stronger acids are less stable, weaker acids are more stable. And so let's take a look at this. Do you know which one's a stronger acid, HNO3 or HCl? You don't have to have it memorized, because on exams you're going to get this. On exams you're going to get the acid-base strength chart. And so if we look at this, the strongest acid on this chart is this one, HClO4, which is called perchloric acid. And then it's just ranked in terms of strength. And so if we start off at the perchloric acid, work our way down, then we see HCl. And then as we go lower, we see HNO3. So it appears from the acid chart that HCl is a stronger acid than HNO3. So HCl is a stronger acid. So I label this SA. S doesn't stand for strong because it doesn't have to be a strong acid. It just has to be a stronger acid. And so we could go from acetic acid to water. Acetic acid is a stronger acid than water, therefore it would be the same thing. So stronger acid. And then HNO3 is a weaker acid. So what we want to do is we want to go stronger to weaker. And so really, this should be pushing backwards, right? This is the favorable direction. And so what we say here is that there is no driving force, no precipitate, no stronger acid to weaker acid, just the opposite here, and no gas formation. Those are the typical driving forces for metathesis or double replacement reactions. And so on tests, you know, what I want you to do is show me why there's no reaction. NR stands for no reaction. But if you just write NR there and you got it wrong, you're not going to get very much partial credit. If you write the potential products here and then maybe cross those out and say, well, there's no driving force, then say no reaction, then you're going to get a lot more credit, a lot more points. And so how I had it written on the previous slide there wasn't good, but that's okay. But there's something else to keep in mind, and that is in Chem 1A, did you learn about the leveling effect? Have you ever heard of the leveling effect? Leveling effect? You never heard of it? Okay. It turns out that this is wrong too. If you wrote this is wrong. Sorry. Well, it doesn't look wrong. That's what's on the chart, right? Is my chart wrong? Do I have them flipped? No, I don't have it flipped. The reason this is wrong is because of the leveling effect. The leveling effect says this: all strong acids in water have equal strength. So all strong acids in water have equal strength, except maybe for H2SO4, which is just slightly stronger. So you can memorize that, but you know, we want to understand a little bit more, you know, because if we understand a little bit more, then we might be able to make predictions or whatever else. And so the next question is that comes up is, why do all strong acids in water have the same strength? And the answer is this. In the gas, this is correct. You know, HCl is a stronger acid than HNO3. And so that's right. Let me just turn this off since we're going to go on a break. And so that means HCl is, you know, what makes a good acid or a stronger acid? Its ability to lose hydrogen, right? In fact, the hydrogen ion. The hydrogen ion is H plus and Cl minus. H plus, what's the composition of H plus? What is H plus made out of? Hydrogen. What's hydrogen normally made out of? Well, it depends on the isotope. If we use the H1 isotope, then the hydrogen 1 atom is made up of 1 proton and 1 electron. If you take away the electron, what are you left with? Proton. And so rather than calling this the hydrogen ion or hydrogen, I'm just going to start calling this the proton. And so we lose a proton here. In fact, Bronsted acid-base reactions are proton transfer reactions, right? All right, so when we compare the two, HCl loses the proton easier. That is, it breaks off easier than HNO3. So it's easier to lose. In water, you know, our protons have what we call extremely high charge density. Their full positive charge concentrated in the volume of a proton. How big is a proton compared to an atom? You know, a proton would be like the nucleus of an atom. And so if we look at a hydrogen atom, let's say a hydrogen atom is as big as a football stadium. If we could blow up a hydrogen atom so it's as big as a football stadium, then how big would the proton be? How big would the nucleus be? Usually, you know, the nucleus is like 10,000 times smaller. And so I have to double check this, but if the hydrogen atom is as big as the football stadium, then the proton would be like a softball or something like that, you know, in size. And so, in other words, it's very small, and it has a full positive charge, meaning it's very reactive. So free protons don't usually exist. You know, if we have a free proton and there's water molecules around, the water molecules will be attacked, or will attack the proton. And so there are two different ways of writing this particular reaction. This is what we call ionization. And ionization is nice, but this is not really accurate. You know, when we have HClAq going to H plus AQ, Cl minus AQ, H plus AQ is kind of unstable. And so what happens is this. The water is going to act as the base here. Because if this is the acid, water is amphoteric, so it can act either as an acid or base. Then the water is going to pluck off that proton to form H3O plus Cl minus here. Well, water is going to have an easier time plucking the proton off HCl than plucking the proton off HNO3, because HCl is a stronger acid. But water has no difficulty plucking the proton off either. And so we know that strong acids are strong electrolytes. So this is 100% ionized, and we call this 100% hydrolyzed. Okay, so we'll come back to this. We'll take a break. Let's take a break until 3:30, and then we'll start up again after that. Or actually, make that 3:35.